Today we're excited to announce the pending launch of our newest exoplanet mission to PSR J1719-14b, aka the Diamond Planet. This video will summarize the goals of this mission, the equipment used, some information about the planet, and finally, how the mission will be accomplished. This mission has three main goals. First, to determine the planet's composition. Second, to map the surface of the planet. Third, to determine if the planet is possibly made of some exotic matter, such as strangelets. We've designed our orbiter with unique equipment optimized for each of these tasks. Here, we'll talk about each instrument and how it helps us achieve our goals. Our orbiter is equipped with a visible spectrometer, which will be pointed at the planet's surface. This uses an Echelle-style diffraction grating to reflect and diffract incoming light, causing spatial separation between wavelengths. This breaks up the light into its spectrum and reveals its spectral line patterns. Using these patterns of dark stripes, we can figure out what kinds of atoms and molecules make up the surface of our planet. The orbiter is also equipped with a wide-field imaging camera, which will be used to periodically take pictures of the planet's surface itself. These images are pieced together to create a map of the entire planet's surface. These kinds of cameras have already been used to map out things like the surface of Mars, as well as by the Hubble Space Telescope, to image portions of our universe in very fine detail. Finally, we'll be using a gamma radiation detection system to test if the planet could have been formed from exotic matter. This system uses charge plates to determine the direction and velocity of gamma photons. On top of the detector is a polymer plate which rejects any low-energy photons, allowing in only the highly energetic gamma radiation. These particles pass through the filter and cause changes in the lower plates, which will be analyzed and converted to velocity, acceleration, and position information. It's theorized that the planet is made from strangelets, a form of matter which converts other nearby matter into strangelets as well. This process releases large amounts of energy, so if this would be occurring, we'd expect gamma photons to be released and detected by our equipment whenever things like meteors impacted the planet. This planet is believed to have been a white dwarf companion to its star, which at the time was merely a regular pulsar star. Because they were so close together, the more massive pulsar began taking matter from its white dwarf companion. This process is known as accretion. Through this accretion, the white dwarf star lost so much mass that it could no longer be considered a star. This is how our planet is thought to have been formed. At this point, you may be asking what happened to all this mass it lost. Well, it ended up in the pulsar star, which, because of the conservation of angular momentum, was sped up to a millisecond pulsar-type star. It is now spinning so quickly that it makes a complete rotation in just a fraction of a second. One of the really cool things about pulsar-type stars is that they are some of the best clocks in the universe. Due to their constant rotation, we're able to detect the slightest changes in the pulse timing caused by a wobble created due to an orbiting object. We use these changes to find out that there was a planet orbiting the star, as well as information such as mass and orbital period of the object, or in this case, our planet. This is a truly crazy planet we've discovered. The planet itself is about as massive as Jupiter, but it's squeezed down to only 6.4% of Jupiter's size. Even though it's that small, it's still bigger than the star. Its size and its mass make it so dense that we think it's primarily made out of crystalline carbon, more commonly known as diamond. Not only that, but the planet is orbiting at a very intimate distance to its star. They're so close together that they could fit easily inside of our own sun. Another consequence of their intimacy is that the planet makes a full orbit of its star in just over 2 hours. You would celebrate New Year's 11 times for each Earth day. We were able to establish a launch pad orbiting the star at the same distance that Earth orbits the Sun, also known as 1 astronomical unit, or 1 AU. This is too far to get a really good look at the planet with all of our instruments, though. What we really want is to be in orbit around the planet itself. To do this, we will use the Hohmann transfer orbit technique. This mission will launch on March 18th, 2016 Earth time, and will arrive on the planet July 23rd, 2016. Once in orbit, our satellite will point itself at the planet's surface and start taking data. Thanks so much for watching, and please stay tuned for more updates on our mission's progress.
Yay, science!